We are now moving into Module 5, the normal distribution. And this is where stats starts to change a little bit. So up until this point, we've done a lot of things that are probably familiar to you. They may be things that you've done in your Math 30 course, in high school, or in other math courses. And now we're going to be moving into something that is more solidly statistics. So this is the normal distribution, and we're going to look at normally distributed variables, areas under the standard normal curve, how we work with them, and then how we assess normality with our normal probability plots. I don't know about you guys, but I love Bridgerton. And the newest season just came out of Bridgerton, and it's going to be about Benedict. But I digress. I did want to start this section, though, talking about how the normal distribution works. And in my thoughts, I was like, well, how could I make this more fun? And so for some of you, this will be fun. For others, you will be groaning, and I apologize. But let's talk about Bridgerton in terms of the normal distribution. So if you don't watch the show, what you should know for context is that young ladies or the debutantes in the society, each season will be presented to Queen Charlotte. And in the group, there will always be one exceptional debutante chosen, and they are referred to as the diamond of the season. And that's the rare gem that outshines the others. So we can apply this to a normal distribution. So you can see here we've got the normal distribution. And down here, we're going to have the less impressive. You could imagine this is, debutante qualities, right? And on the left-hand side here, we've got the less impressive debutantes. If you're a follower of the show, you might find, for example, Penelope or Eloise sort of fall into this category. They're not as charming. Maybe they don't have the best social skills. And then most of the debutantes are going to fall kind of in this mid-range here. And then up on the higher side, you're going to have that one rare gem, the diamond of the season. So it's just like in real life, all of the debutantes have different qualities, but most of them will cluster around sort of the average here, and only a few rare ones will fall to the far right to be the diamond of the season, or to the far left where they're less impressive. So she is the rare standout with exceptional charm, beauty, and poise. And I probably should have started this with dearest gentle reader. An important aspect of any distribution of a variable will be its shape. And we did look at how you can identify the shape of the distribution in previous lessons. And often what we'll do is we'll put a smooth curve over our distribution. And so such curves are called density curves. And they're going to become much more important as we continue through this topic. Some key facts about the basic properties of the density curve is that a density curve is always on or above the horizontal axis, and we call this an asymptote. And property 2, the total area under a density curve and above the horizontal axis is equal to 1. And we're going to use these properties to apply it to some statistical problems. So again, here is a density curve, and it's showing that the total area underneath it is equal to 1. And it's also showing that the density curve is on or above that horizontal axis. So one of the most important uses of the density curve relies on the fact that percentages for the variable are equal to areas under its density curve. And so that's where we're going to take this in terms of calculations. And this leads to key fact 6.2, variables and their density curves. For a variable with a density curve, the percentage of all possible observations of the variable that lie within a specified range equals, at least approximately, the corresponding area under the density curve, and this is expressed as a percentage. And these graphics here illustrate that key fact. So what it's showing is that in the first one here, we'll call this one A, the specified range is to the left of the number. So the percentage of all possible observations of a variable that lie to the left of C equals this area right here expressed as a percentage. And then we'll call this one B. The specified range is to the right of a number. So you can see right here, the area to the right is D, and the percentage of all possible observations of the variable that lie to the right of D equals this area expressed as a percentage. And then we'll call this one C right here. And this is the specified range between two different numbers. And so it's saying that the percentage of all possible observations of the variable that lie between A and B equals the area expressed as a percentage. And so this is going to be what we're going to be working on. This might not make a ton of sense right now, but I promise you when we start to apply it, it will become way more clear. And then I would encourage you to come back and look at this as sort of a definition or an illustration of those key properties. And we can do some practice on that. Now, I pull these ones out specifically because what you're going to find as we move through statistics from this point forward is that sometimes you really need to understand what the question is asking you so that you can answer it. Sometimes it's not very clear. So the percentage of all possible observations of the variable that lies between 5 and 10 equals the area under the density curve between what and what expressed as a percentage. And this is almost a trick. It's between 5 and 10. So if you go back to those properties, we say that it's going to equal the area under the curve between the two numbers expressed as a percentage. The next question is the percentage of all possible observations of the variable that lies to the right of 3 equals the area under its density curve to the right of, and you guessed it, the answer is 3 expressed as a percentage. I typically won't ask you a question like this, but just in case you come across it, this is what they're asking you to do. Let's apply some of the properties for the area under the density curve. The area under the density curve that lies to the left of 5 is 0.354. What percentage of variables are less than 5 and more than 5? And my hint to you is that the area under the curve is equal to 1. So let's draw a little curve here, okay? And we're going to put 5 on here. And we know that the area to the left of 5, so this way, is equal to 0.354. I can't really see the 4. All right, so we know that that's the area. So then what percentage of variables are less than 5? Well, if the whole thing is equal to 1, then we can express the areas as a percentage. So less than 5 is about 35.4%. And I know that because it essentially was given to me. Now, what percentage of the variables are more than 5? All we have to do here is go 1 minus 0.354, and that would represent the area from here all the way over there, and that would be equal to about 0.65 or 65%. So try this for yourself. Less than 5 is simply 0.354. More than 5 is 1 minus 0.354 because the total is 1. And that leads us to the discussion of the normal curve. There's a vast world of data, and it all shares an important characteristic. Their distributions have roughly the same shape. I know that that sounds crazy, but their distributions are known as a normal curve, which is a special type of bell-shaped curve, like the one shown in this picture here. So why do they use the word normal? And that's because it came from the British statistician Carl Pearson. This won't be the last time you hear of our friend Carl. And so they were talking about um, it's quite usual or normal to have a distribution of a wide set of different variables like height, wheat yield, aptitude scores that fall within to this distribution shape. And here are some examples, and I know it seems crazy, but for example, the heights of adult. Most people are of like an average height, and then you'll have some that are very short and some that are very tall. And the more people that you sample, the more likely you're going to get this normal distribution bell curve. We see it in things like height. We see it in exam scores. So there's always going to be a lot that kind of fall within this average, and there'll be some that just really do well and others who don't do well at all. Blood test results. Most people's results for a range of different tests of your blood will show things in an average range. Some will be more extreme than others. And this can be like your cholesterol levels, for example. Social media likes are shown to be a normal distribution. So widgets produced in a factory are mostly this should probably say largest size, and a fewer being a much smaller or much larger. And we see it in stock market returns as well. It is everywhere in the world. And because of that, we can start to use this to solve problems. And we've already talked about it a little bit, but let's go over these important properties of the normal curve in a little bit more detailed. Now, a normal distribution, and then of course its curve, is completely determined by the mean and the standard deviation. And so two normally distributed variables that have the same mean and the same standard deviation will have the same distribution. So a normal distribution is symmetric. So it's going to be like a mirror image on the left and right side. And it is always centered on the mean. So you can see here mu is equal to 6. It's centered on the mean. And the spread of it depends on the standard deviation of the variable. The larger the standard deviation, like this one here, the green line, which has a standard deviation of 2, the more flat and spread out it will be. Whereas you can see the smaller standard deviation of the red line of 0.5, it is not as spread out. Now, a variable is considered to be normally distributed if the shape is like a normal curve. You may recall the three standard deviation rule, which states that almost all observations of the variable lie within three standard deviations to either side of the mean. And that rule is illustrated by there are three normal distributions shown in this figure here. You can see in the green line we are centered on -2, and we've got in the red line, we're centered on 3, and then in the orange line, we're centered on 9. So each normal curve is going to be centered on the mean, and it will spread as far as its standard deviation. But usually, and this is almost universally true, that the normal distribution will fall within three standard deviations of the mean on either side, and that's so negative and positive, and it won't go any further than that. So, for example, if we look at the third normal distribution here, the orange line, we're going to focus in on that guy. What we can do is apply the three standard deviations rule, and so we can end up saying that mu -3 times the standard deviation will be the lower limit, and then mu plus 3 times the standard deviation will be the upper limit. So again, we're focused in on this one here. So all we'd have to do then is put in 9 plus or minus 3 times our standard deviation of 2. I'll put that in brackets so it doesn't look like 32. And you can find that then our lower limit would be 3. So 3, that's where it goes to. And the upper limit would then be 15. And you can see that that's where this one lands on as well. This illustration is just showing the graph of a generic normal distribution, but there are a few things about this figure that go along with the properties, and I'm going to say them again. I'll sound like a broken record, be kind of annoying, but it is a bell shape, okay? It's centered on mu, which is our sample mean, and it is close to the horizontal axis from the range of 3 standard deviations from the mean on the negative side and the positive side. I should turn this into like a little rap or something or a song, but I'm not going to. So once again, the normal curve is bell-shaped. It's centered at the mean and it's plus or minus about 3 standard deviations from the mean on either side. Now, this little bell that I have in here, you guys don't even know how hard it was to find a little bell clip art, but I did. Let's do an example on a normally distributed variable. And in this example, it's heights of female identifying college students. A college has 3,264 female identifying students. The records show that the mean height is 64.4 inches and the standard deviation is 2.4 inches. A, show that the variable height is approximately normally distributed for this population. B, identify the normal curve associated with the variable height for this population. And then C, what is the relationship between the percentage of students whose heights lie within a specified range and the corresponding area under the associated normal curve? So I've split this up into a couple different slides and we'll go through them in the next ones. But from now on, what I want you guys to do when you see a question, and the question has numbers in it that could be useful to you, I want you to start writing them down right away as you read the question. So as I'm reading this, I will write down, for example, n is equal to 3,264, and that I'm going to have a mean of 64.4 and a standard deviation of 2.4. And the reason why I get you to start doing that as you read the question is because you're going to need these things. So it just starts you getting your work in order. You may recall that the first part of the question was show that the variable height is approximately normally distributed for the population. And so what they're asking you to do is to make a histogram or make some sort of a visual. It's most likely going to be a histogram of the relative frequency. So you can see that we've got all the data here in this chart. And what we've done is we've plotted these relative frequencies over here, and we've added a smooth curve around it, and then that will show that the shape of your distribution, and we can see that our shape of the distribution is a pretty nice bell curve. B asked us to identify the normal curve associated with the variable height for this population. So what are they asking you to do? What they're asking you to do is to state your mean and standard deviation, because that will identify our curve for us, because we know that we're always going to be centered on the mean, which in this case is 64.4 inches, and that it's going to spread 2.4 standard deviations away. Finally, it asks what is the relationship between the percentage of students whose heights lie within a specified range and the corresponding area under the normal curve? Well, what it means is that we can approximate the percentage of students that are within a certain height range by looking at the area under the normal curve. And so in this example, say we wanted to find the percentage of students between 67 and 68 inches tall, and you can see that here, 67 to 68, and we've highlighted all of this right here. And if we go and take a line, a dotted line over to the relative frequency, you'll see that it is about 0.0735. And so we can approximate, or we can say that about 7.35% of all the female identifying students are between 67 and 68 inches tall. That brings us to key fact 6.3, normally distributed variables and normal curve areas. For a normally distributed variable, the percentage of all possible observations that lie within any specified range equals the corresponding area under its associated normal curve expressed as a percentage. This result holds approximately for a variable that is approximately normally distributed. And what this means is that percentages of a normally distributed variable are equal to the areas under its associated normal curve. And that's for brevity. Most of the time, that's sort of how it is paraphrased. So let's find areas under the normal curve. But how? So there are so many different normal curves that there'll be one for each mean and standard deviation. Because remember, it's centered on the mean and it spreads out for the standard deviation. So there's infinitely many different types of normal curves. And so a normally distributed variable having a mean of 0 and a standard deviation of 1 is said to have a standard normal distribution. Its associated normal curve is called the standard normal curve. And hopefully, I'm blowing your mind a little bit because this means that what we can do is we can take all of the different sets of data that we have and turn them into z-scores by standardizing them, and then we can compare among the data sets. The standard normal distribution is a variable with a mean of 0 and a standard deviation of 1. And we can standardize a variable by subtracting its mean and then dividing by the standard deviation. So to get your z-score, your z-score, it is your variable x minus mu divided by the standard deviation. And then our resulting variable is called the standardized version of x, or the standardized variable corresponding to x. And here's the fancy box of what I just said. The standardized version of a normally distributed variable for x is found through this formula. And what's so great about this is that you guys already have learned about standardizing scores. You've already learned that the mean is going to be 0 and the standard deviation is going to be 1, and that then we can use this to compare data sets. And here's a cutie little visual for you. I had made my own at one point and it wasn't as professional looking as this one. But for a normally distributed variable, we can find the percentage of all observations in a range if we find the range in terms of their z-score and then determine the area under the standard normal curve. So you might recall that these three distributions that we've looked at, they all have a different mean and standard deviation. But if we take them and we put them into the standardizing formula here, they all become centered on 0 with the standard deviation of 1 on either side. And then using that, we can then determine areas under a standard normal curve. This figure here is showing how you can find percentages for normally distributed variables from areas underneath the standard normal curve. So for example, if you had A and B, then what you can do is standardize the score, and then you'll be able to calculate the area under the standard normal curve. And that's what the next section will be focusing on. Usually I would separate all of these into smaller videos, but for this module, I'm going to just do one really long video because it then corresponds perfectly with the note package without me splitting it up. Please let me know what you prefer. I can split them into smaller sections, or I can just do one long video. Do you remember how I talked about the distribution of data around the world and how it's fun to notice that most of the data we collect can go into the shape of a classic bell curve? Well, this is another fun example. It's a way to look at how mood varies across the week. So on Monday, you start with Monday and you might have the infamous Monday blues. My son and I have a Monday scream session in the car before we go to school. And so most people might rate their mood around like the middle, like a 5 or a 6, if it was on a scale of 10, with only a few feeling extremely sad and a few feeling really happy. And so on Monday, we've got a bell curve. Now, Tuesdays are still pretty average. The pit comes out on Tuesdays, so I'm usually pretty happy about that. But the curve will look similar to Monday, but you might notice that it shifts maybe towards slightly happier moods, sorry. So the average will then center on average to a bit happier. And again, you're only going to see a few that are really upset and a few that are really, really happy. And then we hit Wednesday, and this is midweek. Wednesday's curve starts to shift higher. More people are feeling good. They're thinking, the week is kind of ending. So even though they're feeling better, most people are still going to cluster around the middle, and it will still look like a bell shape. So the middle might be higher in this case. Maybe it's a 7 out of 10. And there'll still be a few extremes. By Thursday, even more people are feeling good. The peak of the curve is higher on the mood scale, but the classic bell shape will still remain. And that shows how most people are still around the average mood for that day. And then we get to Friday, where we've got our weekend vibes. The peak is going to shift noticeably higher. But since most people feel happier, they're still somewhat in the middle. Because remember, we're going to be centered on that mean. A few might be really ecstatic, and then the tails of the curve would show those extreme moods. Saturday is known as our happiness peak. The majority of people are at the high end of the mood scale, but again, you see that bell curve. A few are less happy, and a few are super duper happy. And then by Sunday, oh, we're starting to prepare for Monday, and so the curve is still bell shaped, but we're also seeing the mood kind of go down from there. Most people will be moderately happy, but there'll be a few extreme highs and lows. So the takeaway here is that even though moods change during the week, the bell curve will show up every day. And that's sort of the hallmark of normal distributions. When you collect enough data from a large group, most people are going to cluster around an average, and the extremes are sort of rare. So this is kind of a fun example. And if you want to see another example, I tend to do this every year, but I usually don't teach online except for during COVID. So if you want, email me your height and I will make a distribution of all of our heights and we'll see if it's normal or not. So in practice, a distribution is unlikely to have exactly the shape of a normal curve, but it will be approximately normally distributed. In this section, we're going to learn how to determine areas under the normal curve or the standard normal curve. And there are some properties that I want to go through about this, and you have seen these kind of properties before. The first one is that the total area under the standard normal curve is 1. The standard normal curve is an asymptote, which means that it will extend horizontally above the line. Um, and it will extend indefinitely on both directions, and it will approach but never touch that horizontal axis. Property 3 is that the standard normal curve is symmetric about 0, so the left and right hand sides are mirror images, and almost all the area under the standard normal curve will lie between -3 and 3 standard deviations. Areas under the standard normal curve are so important that we actually have tables for those areas, and we call this the standard normal table, a Z table, sometimes you'll see it be called, or in your case, and within your note package, not your note package, sorry, your formula card package, you will see that we've got table 2, which is the areas under the standard normal curve. And so this is very exciting. You guys now are going to start working with the tables that were associated with that formula card. So you're going to want to pause the video and go grab table 2, the standard normal table. This is in the module 3 section, I believe. And you can also, if you have a textbook, it will be in your textbook, and you can also look it up online. So we're going to look at how we can use the standard normal table or table 2. There are a couple of things about table 2 that I want to talk to you about before we do the example. So if you have your table, you should look at it now, and what you'll see is that you have two sides to the table, and so you've got a left page, and the left page of table 2 is for negative Z scores, and the right page is for our positive Z scores. Now, what you'll find is typically 4 decimal places number that is in the body of that table, and that will give you the area under the standard normal curve. So I can use this one as an example right here. You can see these 4 decimal place numbers in here. These are the areas. And of course, along the column here to the far left, and then the row across the very, very top is the Z score. So this side here, you will find the first 2 numbers of your Z score. So for example, it could be 1.1, and then it could be 1.10. And so then that number would be right here, 1.101, and that would be this number here, and so on from there. So that's sort of the anatomy of your table, but I find it's best to just use it to understand it fully. So in this example here, it's asking you to find the area to the left of the specified Z score. And what we can do is we can often just draw a normal distribution for yourself to help you visualize it. So draw out the normal distribution. You know it's going to be centered on 0, and you can go from -3 to +3. Now, it's asking you to find the area to the left of this Z score. So this Z score is 1.23, so that's denoting that here, and it's the area going to the left of it. So how do we solve that? What you'll find is that if you look at your Z score number of 1.23, and we go into the table and we go to 1.2, and then we go to 3, and match it up here, we get an area of 0.8907. Example 2, finding the area to the right of a specified Z score. So, because the total area under the standard normal curve is 1, the area to the right of 0.77 will equal 1 minus the area to the left of 0.77. And so let's look at, if you have your table 2, make sure you pull it out. And when you're doing that, First, go down the Z column to 0.7, then go across the row to the column that is labeled 0.07. And what you'll reach then is 0.7764. So don't get confused that the Z score in this example and the area are the same. They're the same number, but they won't always be the same. So we used this number here and we looked up this number in the body of the table by finding 0.7 in the first column and then going across the row on the top to 0.07 to reach 0.7764. This is the area under the standard normal curve that lies to the left of 0.77. So that means that the area under the standard normal curve that lies to the right of 0.77 is 1 minus 0.7764, and that is equal to 0.2236. So that means this area here is only 0.2236. In this example, we'll find the area between two specified z-scores. And so we've got z is equal to negative 0.68, 68, sorry, which would be on the left-hand side of your table. And then z is equal to 1.82, and we want to find the area in between them. And so what we'll do is we'll use our table and look up these z-scores so that we can find the area which is located in the body of the table. And then if we want to find the area between them, then what we'll do is we will subtract them. And so if you look it up, you will find these two numbers, subtract them, and the area in between is 0.7173. So make sure that you are actually looking these up with me and doing the practice on these questions. This figure here is illustrating the last three examples that we did. And so what I want to state here is that the z-tables don't give every area, they only give left-hand areas. Everything else is just subtracting from one or subtracting two left-hand areas. You can't ever really find anything new, you're just rearranging areas that are already adding up to one. And students always want to know why, like why do we do it this way? Why is it that if you want to look for an area to the left of Z, you just look in the table, and if you want to find an area to the right, then you have to do 1 minus the area to the left. So the reason is, and it's really simple, they use the left-hand side or areas only because it's one consistent type of area that lets us calculate every other probability just using subtraction. There's nothing special about it. The normal curve is symmetric and probabilities can be found on either side, but choosing to use the left side is just convention and it's not mathematically a necessity. So it's just so that the table is smooth and it goes from 0 to 1 as the Z increases. And that makes the table really easy to read, to build, and for people to check areas. So these are the standard rules that you'll find. If you want to find an area to the left, then all you have to do is just look for your z-score and line that up. If you want to find an area to the right, you must go 1 minus the area to the left, and then shaded in between, you want to find the area between here, then you just subtract them. Here are some notes that I want to mention about table 2 or your standard normal table. So first of all, the standard normal table gives approximate areas under the curve. Also, the area to the left of a z-score is never truly 0 or 1 because the normal curve does extend infinitely in both directions. So the table is just showing us some approximate probabilities. So for example, the first entry in the standard normal table shows 0.0000, and you'll see that there's always that 4 decimal places usually. But the true area is more like 0.0004881, and again, this is infinite, so it will go on forever. I've shown you how to use Table 2 to find areas, but you can do it the other way where you use Table 2 to find the z-scores that correspond to a specified area under the standard normal curve. And so let's look at an example of that. So in this example, find the z-score having a specified area to its left, and we've got the area here of 0.04. So what you have to do, and this feels weird, but this is the method, you search the body of the table for the area 0.04. Yeah, you look right inside the table, in the body of the table. And what you'll find is that there isn't an area in the table that is exactly 0.04. So you'll use the closest thing to it, which is 0.0401. And that then will be the corresponding z-score. So you look in the body of the table and then you match it up over to that first column and that first row. And so the z-score having an area 0.04 to its left under the standard normal curve is roughly negative 1.75. And of course, I wanted to show you this, the previous example with table 2. And so remember, the first step was to search the body of the table for the area 0.04. And we know in this case that there isn't exactly 0.04. So you take the one that is closest to it. And in this case, it's 0.0401. Now, if you have two area entries that are equally close to the one desired, then you take the mean of the two corresponding z-scores as an approximation of the required z-score. So again, first, use any number that exactly matches. Next, use the closest to the desired number. And if you've got two that are equally close, like say these two were equally close, then we would find the mean of that, and then that would become our z-score. And it will often be necessary for us to find the z-score that has a specified area to its right. And we can do this with a special type of notation called z-alpha notation. So the symbol z-alpha is used to denote the z-score that has an area of alpha to its right under the standard normal curve. And so we read it as z sub a or simply z-alpha. Let's do an example, finding the z-score of an area using the special notation z-alpha. In this question, we're going to use table 2 to help us determine z-alpha 0.025. So z-alpha 0.025 is the z-score that has an area of 0.025 to its right under the standard normal curve. And you can see that here in figure A. Because the area to its right is 0.025, the area to the left would then equal 1 minus 0.025, and we would end up with 0.975. So 1 minus 0.025 is equal to 0.975. Now, table 2 has an entry for the area of 0.975, and you can use that to find the corresponding z-score of 1.96. And so consequently, what we'll have is z-alpha 0.025 is equal to 1.96. So again, I encourage you to get your table out to make sure you understand where I'm getting those numbers from. So I broke it up a little bit for us. So Z alpha 0.025. Remember, because the area is to the right and we want the area to the left, we'll take 1 minus 0.025 and that will equal 0.975. Now look in the body of table 2 for the entry of 0.975, and you will get the corresponding z-score of 1.96. Another example of finding the z-score for an area using the special notation of z alpha. And this is a good example because you're going to see that we'll have to take the average here. So for this one here, we want to find Z alpha 0.05. And once again, we want to take our 1 minus 0.05, and we'll end up with 0.95. Now you'll look in the body of the table, and what you'll find is that there are two entries that are equally close to 0.95. They are 0.9495 and 0.9505. So the z-scores corresponding to those two areas are 1.64 and 1.65 respectively. And what we'll do then is take the mean. So 1.64 plus 1.65 divided by 2, and we will find our z-score of 1.645. And we'll do another example here. This is the finding the z-scores for a specified area. So this is finding the two z-scores that divide the area under the standard normal curve into a middle 0.95 area. And so you can see that this section here, this is the 0.95 area, and then we've got the rest making 1, 0.025 on this side and 0.025 on that side here. So the area of the shaded region on the right is 0.025, and we can find the corresponding z-score to be 1.96. Now, because the standard normal curve is symmetric around 0, the z-score on the left is negative 1.96. And so the two required z-scores that we're looking for here will be plus or minus 1.96. So we could also solve this example by first using table 2 to find the z-score on the left, which is negative 1.96, and then applying the symmetry property to get the z-score on the right, which is then 1.96. You now know how to find the percentage of all possible observations of a normally distributed variable that lie within a specified range. But more formally, this is procedure 6.1. So to determine a percentage or probability of a normally distributed variable, here are some steps for you. Step 1, sketch the normal curve that's associated with the variable. It really does help with visualization. Shade the region of interest and then mark its delimiting x values. Next, find the z-scores for those delimiting x values, and then use table 2 to find the area under the standard normal curve delimited by the z-scores that you had already found in the third step. Those steps are illustrated here for you. So again, sketch yourself out a normal curve. You know it's going to center on mu, and the standard deviation will generally be within 3 of the mean. And then you can shade the region that you're interested in looking at, and then mark your delimiting values on here. So in this case, A and B are our values. And then you can find the z-scores for the delimiting x values and use your table to find the area under the standard normal curve. Okay, let's do an example. So this example is on intelligence quotients or IQ. And it's measured on a certain scale, which is normally distributed with a mean of 0 and a standard deviation of 6. And if you're following along and you're working as you're going through this, stop, write down the mean, which is 100, and your standard deviation is 16. It says determine the percentage of people who have IQs between 115 and 140. So let's work through this example. let's follow our steps. First, sketch yourself out a normal curve. Okay. And our mean is 100. So we know that that curve is going to be centered on the mean here. And it's asking us next to then shade the region of interest. So the region of interest is the IQs between 115 and 140. So if this is 100, we're just going to make an assumption that this will be 115 and that 140 will be somewhere over here as those IQs go up on this side. So we can shade that region of interest between 115 and 140. Then we can mark it with the delimiting values, 115, 140 here, and then we can find the z-scores for the delimiting values. And remember, you can calculate these z-scores using the standardizing formula here, which is x minus mu over sigma, or in this case, we would take 115 as our x, minus 100, which is our mean, divided by 16, which is our standard deviation. And so that will give us a z-score of 0.94 for the 115 variable and 2.50 for the 140 variable. So now we've marked out all of our values and we have found the z-scores associated with this area. Now let's use table 2. So we found the z-scores and we can use those to then find the area within the table. So go into your table 2, find 0.94. So of course this is your z-score and you will find an area of 0.8262 and then use your z-score of 2.50 and look up the area and it ends up being 0.9938. And we know that if we want to find the area in between, then we have to simply subtract those areas. So 0.9938 minus 0.8264 is equal to 0.1674. And so our interpretation here is that about 16.74% of all people have an IQ between 115 and 140. Equivalently, we can say that the probability is 0.1674 that a randomly selected person will have an IQ between 115 and 140. And this leads us to visualizing a normal distribution. So as long as we have a distribution who is got a roughly bell shape, then it's true that it will provide the percentages of all possible observations that lie within 1, 2, and 3 standard deviations of either side of the mean. So remember, a z-score tells us how many standard deviations an observation is from the mean. So the percentage of observations within one standard deviation of the mean is equal to the percentage of observations with the z-score between -1 and 1. These properties are referred to collectively as the empirical rule. And we can apply the empirical rule, and we'll find is that for any variable whose distribution is bell-shaped, in particular a normally distributed variable, that approximately 68% of the data will fall within one standard deviation of the mean. 95% of the data will fall within 2 standard deviations of the mean, and 99.7% of data will fall within 3 standard deviations of the mean. So it's a rule of thumb for seeing how data spreads around the mean in a bell curve. And you might be thinking, but Allie, that's the 3 standard deviations rule. We've already learned this. It is and it isn't. The 3 standard deviations rule is like a shorthand version of the empirical rule, and it's focusing only on those 3 standard deviations. So it will say that almost all data falls within 3 standard deviations of the mean. And we use it in statistics because it will help us to identify outliers and it kind of gives us a quick estimate of how extreme a value is. But there is a key difference here. The empirical rule covers 1 standard deviation, 2 standard deviation, and 3 standard deviation, giving a detailed picture of data spread, whereas the 3 standard deviations rule will only focus on the extremes of it. And so, in that way, we often will be referring to the empirical rule because it's a lot more focused. The next 3 slides are going to demonstrate the empirical rule, and we're going to apply the empirical rule to IQs. So recall that IQs are normally distributed with a mean of 100 and a standard deviation of 16. And so, property one of the empirical rule states that approximately 68% of all people have IQs within 1 standard deviation to either side of the mean, which means we will be able to find the approximate values of the IQs that are within that 1 standard deviation. And so, we'll take mu plus or minus 1 times our standard deviation. And the 1 isn't in here because you don't have to put it in there. It's an automatic assumption when it comes with 1. With 2 and 3, though, you will put the 2 in, you will put the 3 in. So what we'll do is mu 100 minus 16 is equal to 84. Okay, so that's the lower limit of the IQs. And then 100 plus 16 times 1, which is 16, is equal to 116. And so the interpretation here is that 68.26% of all people have IQs between 84 and 116. Property 2 of the empirical rule states that approximately 95% of all people have IQs within 2 standard deviations of the mean. And so what we can do is mu plus or minus 2 times our standard deviation. So on the lower end, 100 minus 16 times 2 is equal to 68. And then 100 plus 16 times 2 is equal to 132. And so the interpretation here is that approximately 95.44% of all people have IQs between 68 and 132. Property 3 of the empirical rule states that approximately 99.7% of all people have IQs within 3 standard deviations to either side of the mean. So that is mu plus or minus 3 times the standard deviation. So on the lower end, we'll have 100 minus 16 times 3, which is equal to 52. And 100 plus 16 times 3 is 148. And so the interpretation here is that approximately 99.7% of all people have IQs between 52 and 148. And so this is just showing that the empirical rule allows us to quickly and easily get useful information about a variable that might have a roughly bell shape. It will show us how to determine, at least to some approximation, the percentage of all observations of a variable that can lie within 1, 2, or 3 standard deviations from the mean. For a normally distributed variable, we can get percentages for any number of standard deviations by using table 2. We can apply that table and find normally distributed variables for things that are within, say, 1.5 standard deviations to either side of the mean. And here's a graphical display of the empirical rule for IQs that we just looked at, and it shows you information about a normally distributed variable extremely quickly and extremely easy. Now, the one thing I want you to note is that 3 standard deviations of the mean has the biggest range because most people are going to fall between 52 and 148. 52 is a quite low IQ, and 148 is a really, really high IQ. And of course, 99.7% of the population is going to fall within there somewhere. Even Einstein would fall in here because I think his IQ is like 145. So, in the last procedure, we were able to determine the percentage of all possible observations of a normally distributed variable that lie within any specified range. But there will be times where we want to carry out the reverse procedure, and that is to find the observations corresponding to a specified percentage. The procedure looks really similar. So this is procedure 6.2 to determine the observations corresponding to a specified percentage or probability for a normally distributed variable. First, sketch the normal curve associated with your variable, shade the region of interest, use table 2 to determine the z-scores that are delimiting the region, and then find the x values having the z-scores that you had found in the step from above. And this is a note for you guys. This isn't on your formula card, but feel free to add it. It's your equation to find a z-score, but it's transposed so that then you can find each x value from its z-score. So the formula here is going to be equal to mu plus your z-score multiplied by your standard deviation, respectively. This is an example about how to obtain a percentile for a normally distributed variable. And often you will see percentiles denoted as a capital P, and then it will have whichever percentile you're looking for in subscript. So you can see in this situation, we want to obtain and interpret the 90th percentile for IQs, and that will always be denoted in this case percentile of 0.90. So the 90th percentile is the IQ that is higher than those of 90% of the all people. We know that IQ is normally distributed, and because of that, then we can determine the 90th percentile by using our procedure. So first, you can see it started out with the sketching the normal curve. It's centered on our mean, which is 100, and its spread or its standard deviation is 16. And then we shaded the area of interest here. We're looking for the 90th percentile. So we're looking for 90% of the people. So you can see it's 90 and then down from there. Everybody from here and down. Now, the z-score corresponding to the percentile 0.90 is the one having an area of 0.90 to its left under the standard normal curve. And so if you look at your table 2 or your standard normal table, that z-score is 1.28. And again, I encourage you to stop, to go ahead to look in your table and make sure you understand where I get 1.28 from. I'm not showing the table purposely because I find that if I show it, most of the time you'll look at it and go, yeah, I know how to use it, and then you don't actually try. When I'm teaching in person, which is I don't usually teach online, when I'm teaching in person, I would force math on you and I would make you look this up in front of me. So I guess you lucked out this time. So we left off before I went on my little rant. I'm sorry about that. And we want to find that the Z score, and that is 1.28. But we want to find the X value having the Z score 1.28. The IQ, that is 1.28 standard deviations above the mean. And of course, the mean is 100. So if we did 100 using our formula, 100 plus 1.28 times 16, then we get 120.48. And so the interpretation here is that the 90th percentile for IQs is 120.48. Thus, 90% of people have IQs below that, and 10% have IQs above that. And what you can see down here is this is that transposed equation. They don't show the steps of transposing it, but you guys have that formula on the other slide. And again, write it down on your formula card. I don't mind. In this section, we're going to talk about how we assess normality using a normal probability plot. And I'm going to go through this, but we will get lots more practice with this type of thing in lab. Now, the idea behind the normal probability plot is really simple. You compare the observed values or the values that you have of a variable to the observations expected from a normally distributed variable. And we use a normal probability plot to do that. And what you guys will find in lab is that we call it a QQ plot. And so this is a plot of the observed values of the variable versus normal scores or observations expected for a variable having the standard normal distribution. And so if that variable is normal, the normal probability plot should be roughly linear and vice versa. And we'll know if it's not linear, then it's probably not normal. So when you use a normal probability plot to assess normality of a variable, you have to remember that you're making a decision of whether a normal probability plot is roughly linear, and that's subjective, and that you're using a sample of observations of the variable to make a judgment about all of the possible observations of the variable. And of course, that's going to become more important as we move into inferential statistics. These are the guidelines for assessing normality using a normal probability plot. So, to assess the normality of a variable using sample data, construct a normal probability plot. If it is roughly linear, you can assume that there's an approximately normal distribution. If the plot is not linear or roughly linear, then you can assume the variable is not normally distributed. And these guidelines should be interpreted loosely for small samples, but it's pretty dead on for a larger sample. And of course, you're going to have that cutie little bell shape. So we need to look at what I'm talking about. So when you guys do your normal probability plots or you do your QQ plots in lab, what you'll find is that you will generate something that looks like this, where you've got data points and you'll have a line. And that's what we're talking about with the roughly linear. You're comparing the values that you actually observed with ones that you would expect that to be from that normal distribution. And then you look to see if that is roughly linear, which again is a bit subjective. You use a sample of observations, and then you can take this to make a judgment about all of the possible outcomes that you have. I'll show you guys a quick little example of this. So in this example, we've got adjusted gross income. This table shows a sample of tax returns, and it's saying to construct a normal probability plot to assess the normality of it. And this is a simple random sample of just 12 returns. So that's a pretty small sample size. And when you look at a table like this, it's really hard to know what kind of a distribution this is going to fall into. But of course, we can make our normal probability plot. Okay, so a normal probability plot was constructed here. To do that, you would arrange your data in increasing order. You would get the normal scores from it, and then what you would do is you would plot the points using the horizontal axis for the adjusted gross incomes and your vertical axes for your normal scores. And then what you'll get is something like this. Now, the question is this roughly normal? And what we'll do is we will draw a trend line on here. And I'll get my little pen out. I'll do a different color. And this is the line. Now, what you're looking for is for your points to cluster around this line. And if it does, then it's considered to be relatively normal. But for this one here, it doesn't follow that line at all. And so last year's adjusted gross incomes are not approximately normally distributed. One of the main uses for these normal probability plots, aside from assessing normality, is to look for outliers, which you guys know is an observation that falls well outside the overall pattern of data. And so you can see in this example here that we've got a line And this is approximately normally distributed because it falls, it clusters around that line, except for this one point right here. And because there's just that one point there, it's an outlier. It falls outside the overall pattern of the plot. Now, in lab, I'm also going to teach you how to calculate a Shapiro-Wilk, which will tell you if something is normal or not based on a statistical test.